Welcome to today's Explainer. Have you ever just stared at a carton of milk and wondered how we actually guarantee it's safe to drink? Well, today we're looking into the invisible science that secures our global food supply. Specifically, we're breaking down the sheer ingenuity of the alkaline phosphatase test. It's a genuinely brilliant bit of chemistry, so let's get right into it.
So here's our roadmap for today. First, we'll look at the pasteurization puzzle. Second, the chemical clue. Third, setting up the lab. And finally, the step-by-step procedure. All right, let's dive right into Section 1, the pasteurization puzzle.
Think about it. Once raw milk goes through all that heavy heating machinery at a dairy plant, it honestly looks exactly the same as it did before it went in. We obviously can't see microscopic pathogens with the naked eye, right? So how do we actually know that pasteurized milk is safe and free from those bugs? How do dairy scientists absolutely guarantee the heating process worked before shipping it off to your local grocery store?
Well, we essentially have a dual goal here. First up, we need to confirm adequate pasteurization, literally proving the milk reached the right temperature for the correct amount of time. But the second goal, it's just as critical. We have to detect any post-processing raw milk contamination. Just imagine if the pasteurization worked perfectly, but then later down the assembly line, just a tiny splash of unpasteurized raw milk accidentally got mixed into that safe batch. It happens, so our test needs to be powerful and sensitive enough to catch that too.
Moving right along to Section 2, the chemical clue.
Okay, meet our primary suspect in this mystery, alkaline phosphatase. Now, this is an enzyme that is naturally present in raw milk. But here is the absolute genius part of this whole thing. This enzyme is conveniently destroyed at a temperature just near the pasteurization point. It's almost like nature engineered a built-in microscopic thermometer just for us. So, if this enzyme somehow survives the heating process and we find it in the final product, well, it tells us definitively that the pasteurization process failed.
This brilliantly illustrates how the chemistry actually works, and it's based on a super elegant principle utilized by a scientist named Scherer way back in 1943. On the left side, with raw milk, the enzyme is still present. When we introduce a very specific chemical, disodium para-nitrophenol phosphate, the enzyme attacks it. It liberates a compound called phenol, and that forms a very distinct yellow-colored complex in an alkaline pH. But look at the pasteurized milk side on the right. The enzyme has been completely destroyed by the heat, and because it's destroyed, no phenol is liberated. Crucially, there is no yellow color. The milk just stays its normal color.
The crucial takeaway here is this: the intensity of that yellow color is directly proportional to the activity of the enzyme. It's not just a simple yes or no test, which is awesome. If the tested milk turns a bright deep yellow, there is a massive amount of active enzyme in there. That means a major pasteurization failure or a pretty large amount of raw milk contamination. But if it's just a very faint, pale yellow, it might just be a tiny, accidental drop of raw milk. This gives our scientists a direct, measurable, visual clue.
Okay, let's get our hands dirty. Section 3, setting up the lab.
So here's our essential apparatus, and as you'll see, it is highly specific to ensure total accuracy. We need a thermostatically controlled water bath kept strictly at 37 degrees Celsius, give or take just 1 degree. We're going to need a LavaBond comparator, equipped with standard color discs. This is the special device we use to precisely measure that yellow color we just talked about. We also need standard test tubes, exactly 16 by 1.50 millimeters, with tightly fitting rubber stoppers. Toss in some accurate pipettes in 1, 5, and 10 milliliter sizes, Wattman No. 2 filter paper, and some litmus paper. All this specialized equipment makes absolutely sure our test is perfectly repeatable every single time.
Now, our reagents are what actually make this whole reaction happen. The first one is a sodium carbonate bicarbonate buffer mixed with distilled water. This one is pretty easygoing. It can safely be stored right at room temperature. But notice the second one here, the buffer substrate. This is the solution containing that disodium p-nitrophosphate we mentioned earlier. And wow, is it highly sensitive. It's only stable for about 1 month, and it literally must be stored in a refrigerator at 4 degrees Celsius or colder. It's actually so sensitive that you have to run a strict color control test on it if it's been in storage, just to be absolutely certain it hasn't degraded before you even think about testing the actual milk.
All right, the moment of truth. Section 4, the step-by-step procedure.
The procedure begins with some very careful measured steps. First, we pipette 5 milliliters of our highly sensitive buffer substrate and 1 milliliter of the test milk into a tube, stopper it tightly, and mix it thoroughly by inversion.
But step 2 is where the scientific method really shines, in my opinion. We prepare a control tube at the exact same time. We mix 5 milliliters of the buffer substrate with 1 milliliter of boiled milk of the exact same kind we're testing. Why boiled? Well, boiling the milk destroys all the enzymes entirely, which gives us an absolute zero baseline to compare against. Finally, step 3, both of these tubes go right into our 37 degrees Celsius water bath.
And now we play the waiting game. We have to incubate those tubes in the bath for exactly 2 hours. We literally cannot rush this process. We need to give that chemical reaction in the 37-degree heat enough time to fully develop. If that sneaky alkaline phosphatase enzyme is hiding out in our test sample, those 2 hours will force it to show its hand, liberate that phenyl, and start turning the whole solution yellow.
Okay, 2 hours later, it's time for the final reveal. We carefully pull the tubes from the bath and invert them. Next, we place our boiled milk control tube on the left side of our Lovabond comparator stand and our test sample right next to it on the right. Then we just read the developed color against those standard calibrated discs. Now, here's a pro tip. It is absolutely vital that if we are doing this indoors under artificial light, we must use an approved daylight source of illumination. Otherwise, the yellow color gets visually distorted and ruins our reading. Finally, we record the readings, adding a plus or minus sign to the figure of the nearest standard color disc. This documents exactly how much enzyme activity occurred.
But, any good detective has to know the exact limits of their investigative tools. There is one major exception to everything we've just discussed. This test is completely inapplicable to sour milk or milk preserved with chemical preservatives. Those specific conditions actually alter the chemical environment and the pH, which would totally ruin the reaction and give us a completely false reading. So it's a highly precise tool, but only effective when used under the exact right conditions.
Which brings us to our final thought for today's explainer. Next time you pour yourself a cold glass of milk, will you think about the invisible enzymes, the 37-degree water baths, and the strict lab protocols ensuring its safety? Behind almost every simple product sitting in your fridge right now is a rigorous, fascinating world of food science working quietly behind the scenes. Keep wondering, keep learning, and keep exploring the incredible chemistry all around you.